So today we're going to talk about logarithmic functions. So we're in section 3.2. All right, so let's get started. So we're going to talk about a new function for a couple of years. This was out of the topics in Algebra 2. So last year was one of the years that was out of Algebra 2. So this is probably something that you guys haven't seen before. What we're looking at with logarithmic functions? A lot of people think that they're confusing. That they're hard. It's a lot like when we worked with inverse trig functions, where you have to think in a little bit different way, and it might take a little bit of work with them for logarithmic functions to start kind of making sense. So if it seems confusing at first, don't worry, just stick with it, and they'll start making sense, just like we did at the beginning of the year with the trig functions and the unit circle, that kind of thing. The more we worked with it, the more familiar we became with it. So the idea of a logarithmic function. The logarithmic function is the inverse function of exponential functions. So we know that exponential functions, if we look at their graph, the graph of an exponential function looks, just a quick sketch, looks something like this. So exponential function, the graph passes the horizontal line test and the vertical line test. So our function, exponential functions are functions, and because it passed the horizontal line test, they have an inverse. So the logarithmic function is the inverse function of the exponential function. And just like the exponential function, we have different bases for exponential functions. We're going to have different bases for our logarithmic functions. And the way we write these is we say that f of x equals the log to the base a of x. And x has to be greater than 0. We can't take the log of a negative number, and a is greater than 0, and a doesn't equal 1. So just like we did with the exponential function, we don't want a to be 1. We want some other number for our base.
That's log ax.
Log to the base a of x is how we say that. I'll write that out. Yeah. Our log, we can have a fraction as a base, just like we had a fraction for a base for our exponential function. But we don't want our base to be 1. So I'll write this, we say log base a of x. So that's how we say it. And we'll work with a couple of bases more frequently, and we'll get to those today. And those have a special name, and we'll give those a special name. And we said that the logarithmic function is the inverse function of the exponential function. So what we're saying is that y is log to the base a of x if and only if a to the y equals x. So this is how they undo each other. The log to the base a of x is y, tells us that a to the power of y equals x. And when our function is written in this form, we call this logarithmic form. And we call this form exponential form. So this is how the exponential function and the logarithmic function undo each other. Now, one way that can be helpful to think about the logarithmic function is when you see log base a, you can think power of a. So this is like asking a question. What is the power of a that gives you x? A to what power equals x? So if you think of the logarithmic function as saying what power or power of, that can help you think about these. Now, I said we have a couple of bases that we're going to work with more. Normally, our number system, we use base 10 number system. So one of the more common logarithms is the log base 10. And if we look at the log base 10, that's the only time we don't write the base under our logarithmic function. So if we're working in base 10, we just write log of x. And on your calculator, there's a button that says log. The log button on your calculator calculates the log base 10. And what this is telling us is what power of 10 gives us the number x. So let's look at a couple of examples of switching from logarithmic form to exponential form, just to get an idea of how we switch back and forth. So if we have log to the base 2 of 8, and we want to change this, log to the base 2 of 8 equals 3. So here's our logarithmic form. We want to write this in exponential form. I'm going to do these in columns. So this is logarithmic form. This is telling us that the power of 2 that gives us 8 is 3. So if we write that in exponential form, we would say 2 to the 3 equals 8. The power of 2 that gives us 8 is 3. 2 times 2 is 4, times 2 is 8. 2 to the third power is 8. The log to the base 2 of 0.25, and I'm going to rewrite that as log to base 2 of 1/4. And this is minus 2. This is telling us that the power of 2 that gives us 0.25 is negative 2, or the power of 2 that gives us 1/4 is negative 2. So in exponential form, this would be 2 to the negative 2 equals 1/4. Log to the base 3 of 81 equals 4. This is telling us that the power of 3 that gives us 81 is the 4th power. In exponential form, that's 3 to the 4 equals 81. And if we're looking at log base 10, let's look at a couple of these in log base 10, because those are the more common logarithms. So we'll look at a couple of examples. Log the base 10 of 1/1000 equals -3. This tells us that the power of 10 that gives us 1/1000 is the -3rd power. So in exponential form, this is 10 to -3 equals 1/1000. Yes? 1/1000. You could write that as a decimal. Usually with exponents, it's a little easier to see if you leave it as a fraction, because it's a little easier to see that 10 to the 3rd is 1000, then 10 to the -3 is 0.001. It's a little easier to visualize. Right, so in scientific notation, that is definitely the case, yes. So that's an example of log base 10. Let's look at log base 16 of 8 equals 3/4. That tells us that the power of 16 that gives us 8 is 3/4. So in exponential form, this would be 16 to the 3/4 equals 8. Questions on switching from exponential to logarithmic form? So this is a big part of what we're going to do today, is just getting familiar today, and actually Friday. We're going to practice some more with this on Friday. Is just getting familiar with what do logarithms mean? What do they tell us? So let's talk about some of the properties of logarithmic functions. And when we talk about these, as I'm doing notes, I'm using logarithmic function just to be more formal. When we talk about them, we'll usually refer to them as log functions. We can use use shorthand and call them log functions. So our properties, and these come straight from how we define them, and these are important ones to remember. The log to the base a of 1. Any base is always 0, because any number to the 0 power, this is the same as saying a to the 0 equals 1. Any number to the 0 power equals 1. So our second property, log to the base a of a is 1. The power of a that gives us a is 1. This is the same as saying a to the 1 equals a. And we said that the logarithmic function and the exponential function undo each other, or they're inverse functions, so they undo each other, just like the square and the square root function, the multiplication undoes division. So if we have the log to the base a of a to the x, that just gives us x. The logarithmic function and the exponential function give us x. The power on a that gives us a to the x is x. And this is also the same as saying that a to the log base a of x is x. The logarithmic function and exponential function undo each other. So this is the logarithmic function. This is the exponential function. We have the same base, so they undo each other. We just end up with x. And our fourth property is that if the log base a of x equals the log base a of y, then x equals y. It's kind of like they cancel each other out. It's not exactly canceling each other out, but that's kind of how it works out. So if we have the same base and the two logs are equal to each other, then the number inside of whatever's inside of our function equals each other also. So these are some properties of our logarithmic functions. So let's do a couple of examples working with these. And then we'll talk about graphing exponential functions. If we have log to the base 5 of x equals log to the base 5 of 8, this tells us that x equals 8. So if we have an equation like this, this is how we would solve an equation. And we'll do more complicated logarithmic equations a little later in the chapter. And if we have an equation like log to the base 5 of 1 equals x. So remember, this question is asking us what power of 5 gives us 1, and whatever that power is x. So what power on any number gives us 1? 0. So this tells us x equals 0. And that's because 5 to the 0 equals 1. So the logarithm is asking us what exponent do we have to put on 5 to give us this number. Questions on that so far? All right, before we talk about graphing, I want to do a couple of examples of going from exponential functions, exponential form to logarithmic form. So doing the opposite of what we did on our first examples, just so we're a little bit familiar with doing that. So we're going to go from exponential form to logarithmic form. So we're going the opposite direction we did on our first examples. If we have 8 squared equals 64, and we want to write that in logarithmic form, what is our base here? Our base? Our base is the thing that we're raising to an exponent. Our base is 8. Our exponent is 2. This, if we want to change this to logarithmic form, so whatever we're raising to the exponent is our base. So in logarithmic form, we're talking about log base 8 of 64 equals 2. The power of 8 that gives us 64 is 2. That's what these two are saying, the same thing. 9, let's say we have 9 to the 3 halves equals 27. So what's our base here? Our base is 9. That's the thing that we're raising to a power. So we have log base 9 of 27 equals 3 halves. 9 raised to the 3 halves equals 27. Here, this is kind of what you were talking about earlier, Cedric. In exponential form, I'm going to say 10 to the minus 3 equals 0.001. So what's our base here? 10. 10 is the number we're raising to an exponent. When we write log base 10, we don't have to write the 10 there. So the log of 0.001 equals -3. If there's no base here, we're assuming that we're talking about base 10. 10 to the negative 3 power equals 0.001. Let's look at one with variables. U to the V equals W. What's our base here? U. So we have log base U of W equals V. U to the V power equals W. So just a few examples of going the other direction from exponential form to logarithmic form. Whatever the number is that we're raising to the power is our base. All right, questions before we move on. All right, let's talk about the graphs of logarithmic functions. So our graphs, what do our graphs look like? What do we know about graphs? So because the logarithmic function is the inverse of the exponential function, we can figure a few things out about its graph. The domain, is 0 to infinity. And we're saying x is greater than 0. So we have to, in order to evaluate a logarithmic function, the number that we're putting in has to be bigger than 0. We can't put a 0 in, and we can't put a negative number in. Oops, my thingy died here. All right, so the number that we plug in has to be bigger than 0 for our logarithmic function. Our range. The range, the numbers that we get out of the logarithmic function is there we go. The range is minus infinity to infinity. So the numbers that we get out can be anywhere from minus infinity to infinity. The x-intercept. So our exponential function had a y-intercept. Because we're talking about the inverse function, we have an x-intercept. The x-intercept of any exponential function is 1, 0. So it's going to intercept the x-axis at x equals 1. Whatever the number is inside my function, whenever that equals 1, is where it's going to intercept the x-axis.
Always?
Always. So if we have some complicated thing inside of our logarithmic function, whenever that thing equals 1 is where it's going to intercept the x-axis. The y-axis is a vertical asymptote. The vertical asymptote at x equals 0. So our exponential function had a horizontal asymptote at y equals 0. Our logarithmic function has a vertical asymptote at x equals 0, or the y-axis. X equals 0 and the y-axis are the same thing. And our function is increasing if a is greater than 0. So our function increases for positive bases. So let's graph one exponential or one logarithmic function to get an idea of what they look like. And they're all, like exponential functions, they all look very similar. So we're just going to graph one. Let me set up a new page here. So here are our axes. And we're going to graph y equals, f of x equals log base 2 of x. So we're going to make a chart, make a table of values, and plug in a few numbers to get our graph. Now we know that the x-intercept, so let me put some points on here. We know that our x-intercept is 1, 0, so we have a point here at 1 on the x-axis. And I'm going to make a table, so here's x and here's log 2 of x. And we'll plot a few points to get an idea of what this looks like. We know that the y-axis is a vertical asymptote. So if we graph x equals 1/2, this is telling us the log to the base 2 of 1/2. We want to know what power of 2 gives us 1/2. That's -1. 2 to the -1 is 1/2. So over here, down here at 1/2, we have a point at -1. If x equals 2, the power of 2 that gives us 2 is 1. So here at x equals 2, my graph goes up to here. And we'll go jump to 4. The power of 2 that gives us 4 is 2. So over here at 4, we're up here at 2. So our function, our logarithmic function, looks like this. And the y-axis, x equals 0, is our vertical asymptote, so it never gets to 0. It's just going to keep going down, 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 down. And it's going to keep increasing. It goes very slowly up. But this is what all the graphs of all logarithmic functions look like, something like this. And if we remember that our exponential function looked like, tangle here. Our exponential function looked something like this. And this is a reflection of the exponential function over the line y equals x. So if we reflect over the line, this is an exponential function, this is my logarithmic function. And like logarithmic functions, our exponential functions, our logarithmic functions transform just like any other function. So let's talk a little bit about transformations. I'm not going to graph a lot of transformations. You guys are good with transformations already, yes?
So to get do you just plug those numbers into your calculator? So like if you did x, would you just plug that in?
Well, our calculator, we'll talk about how we use these with our calculator on Monday, our calculator won't give us log base 2. So what I did here, log base 2 of 1/2, I said what power of 2 gives me 1/2? And I know that 2 to the -1 is the same as 1/2. So I just because I know how exponents work, we know how properties of exponents. 2 to the -1 gives me 1/2. I know that the power of 2 that gives me 2 is 1. 2 to the 1 equals 2. So I was just using what we know about exponents to come up with these points. All right. And I was wondering about Abraham Lincoln. Is it Abraham Lincoln? Didn't you play Abraham Lincoln? You got an award this morning.
Yeah.
Yeah.
Oh yeah. It
Yeah.
was,
What's the story with Abraham Lincoln?
It was Mark Twain.
Mark Twain. Okay. I got the name. So you
We're doing like this court thing.
okay, and you were Mark Twain?
Cool. I won the case.
Nice. All right, so transformations. So our logarithmic functions transform just like any other function. So I'll give you some examples here. So they transform just like any other function. So some examples. And one thing to remember about the transformations of logarithmic functions, if the graph shifts left or right, our intercepts in our asymptote shift left and right also. Because we have a vertical asymptote, our asymptote is going to shift just like our function does. Well, if we're shifting up and down, because it's a vertical asymptote, that doesn't matter. A shift up and down is just going to be, it's going to have the same vertical asymptote. So the asymptote and intercept shift left or right with our function. So if we start with, if we're talking about our function, I'm just going to write a couple of examples. If we have y equals, we'll just use log base 10, y equals log of x, y equals log of x plus 2 is going to be a shift to left. If we say y is log of x plus 2 minus 3, that's going to be 2 left and 3 down. Just like any other function, just like we've done transformations before, if we have y equals minus log of x, that's going to reflect over the x-axis. And if we have y equals the log of minus x, that's going to reflect over the y-axis. So just like any other function. So if your problem asks you about how the graph looks, or to sketch a different graph based on these transformations, the graph that we sketched earlier, that graph would translate, move around, just like we've done with other functions. Same kind of idea with transformations. So I'm not going to do a lot of work with those because you guys are already good with those. All right, any questions? We have one last quick topic to talk about, and then we'll be done. So we said during our last class that the e, the number e, comes up in a lot of context. We call that our natural base. So we're going to use that as our natural base for our logarithmic function also. So when we use base e, we have the natural logarithmic function. The important thing to remember about the natural logarithmic function is that our base equals our constant e that we talked about the other day that came up with continuously compounded interest. So our base is e. The way we write it is f of x equals ln x. ln means natural logarithm. And your calculator has an ln button. So that's the two kinds of logs that our calculator can calculate, are base 10 and the natural logarithms. So if you're asked to calculate something, it's either going to have to be in base 10 or in the natural logarithm. And if it's not, we'll learn how to switch them around, I think on Mondays when we talk about that. So just a couple of examples. All the properties are exactly the same for the natural logarithm as the other logarithmic functions. We're just using base e. You can think about the natural log as log to the base e of x. It just comes up so often we give it a special symbol. Instead of calling it log base e, we call it natural log. So it's important to remember that when you see ln, that means log base e. So let's look at a couple of examples using the natural logarithmic function, going back and forth between exponential and logarithmic form, exactly the same for the natural base as the other examples we did. We just have e as our base. Let's look at a couple of important properties. The natural log, or not properties, examples. Natural log of e to the fifth. Natural log of e to the fifth. Anybody tell me what that's going to be? Natural log is log to the base e. So what power do I have to raise e to get e to the fifth? 5. Log to the base, natural log of e to the fifth is 5. And remember that these are inverse functions. The natural log and the exponential function are inverse functions. They undo each other. So these are inverse functions. Natural or e to the natural log of 3 is going to be 3. This is our exponential base. This is our logarithmic function. These are inverse functions. They undo each other. And if I want to look at the natural log of 1 over e squared, I can rewrite this as the natural log of e to the minus 2. And this is just minus 2. They're inverse functions. They undo each other. A couple more examples with this. Just going back and forth between logarithmic and exponential form. If I have the natural log of 4 equals 1.386. This is the same as saying e to the 1.386 equals 4. Remember that I said the logarithm, you can think of logarithm as the power of e that gives you 4 is 1.386. That tells me e to the 1.386 equals 4. And if I go the other way, e to the 1/2 equals 1.6487. This is the same as saying the natural log of 1.6487 equals 1/2. So these are just like our examples earlier, except using our natural base. Any questions on that? All right, one more kind of homework problem that you're going to see that I just want to talk about really quickly, not a new topic, but if your problem asks you to find the domain of a particular function. So let's say, and you'll see a few of these in your homework. If we want to find the domain of the natural log of x plus 3. Now remember we said that the domain of the logarithmic function was our number, whatever we plugged in, has to be greater than 0. So whatever's inside our function has to be greater than 0. So to find our domain, I say that x plus 3 has to be x plus 3 has to be greater than 0. Whatever we plug into our function has to be bigger than 0. And if I solve this, I get x has to be greater than negative 3. So our domain for this function would be all x greater than negative 3, because I can't plug 0 or a negative number in here. So as long as this whole thing is greater than 0, I'm okay. So let's look at one more example of that. If we have find the domain of log of 2x minus 5, whatever we plug in here has to be bigger than 0. Whatever we take the log of has to be bigger than 0. So this says 2x minus 5 has to be greater than 0. So 2x is greater than 5, and x is greater than 5/2. So our domain for this function would be x greater than 5/2. So that's all you have to worry about when you're thinking of the domain, is whatever I plug in here has to be bigger than 0. All right, any questions? Okay. Homework. Page 216. All right, there you go.
That's 55.
That's a 55, yes.